Alright, how's it going, guys? So sorry I couldn't be there today, but as someone said somewhere at some point in time, the show must go on, so you guys are going to be learning about organic reactions. So the first one that we have right here is, well, we're revisiting it, let's just say that. So we have combustion reactions. Now, at one point, I think it was during thermochemistry, we looked at the difference between our complete, no, we didn't use complete, open system and closed system combustion reactions. Those are the words I was looking for. Now we're just going to expand on that a little bit with a complete combustion and an incomplete combustion. So for a complete combustion, this is technically what we've always been doing. And that when we have a complete combustion reaction, the products are always going to be carbon dioxide and water, vapor, or liquid, depending if it's an open system or a closed system. So these were the reactions that you have been doing since you first learned about combustion reactions. So if we want to show like the combustion of pentane, now we can draw out pentane, and we can even write the chemical formula because it's an alkane. The chemical formula is CnH2n plus 2. So if we have 5 carbons, we know it's going to be C5H12. Then of course for combustion reactions, we react with oxygen gas, we produce CO2, and of course H2O. Now, in this one right here, it's not specifying if it's an open or a closed system, so we assume open system, which water will be a gas. Now, if we have this organic reaction, all we need to do is balance it. So to balance, we have a 5 in front of carbon, a 6 in front of H2O, and then an 8 in front of oxygen. Now, for our incomplete combustion reactions. So these here are a little different. Now, the thing is with an incomplete combustion reaction, you'll never be asked to actually write out the incomplete combustion reaction. It's for the most part, it's recognizing when we have an incomplete combustion reaction. So, we're going to recognize that we're going to have an incomplete combustion reaction. We are still going to get carbon dioxide, all right, but we're also going to get carbon monoxide and or carbon solid, and of course water, vapor, or liquid. So we get a combination of basically these 3 things that have carbon in it. Now, we can get one where it's only carbon monoxide, one where it's carbon dioxide and carbon monoxide, one where it's all 3, right? So it's just a matter of recognizing when we have something other than carbon dioxide, it is an incomplete. So let's look at this reaction right here. So the incomplete combustion reaction only producing carbon monoxide and water vapor of 2,2,4-trimethylpentane. All right, sorry about that cough. All right, so same thing, we can draw out our 2,2,4-trimethylpentane if we want to, or we can just go straight to the chemical formula. Now in this case right here, it's still an alkane. It's still in the same formula as above, CnH2n plus 2, except where we have those 3 branches, that's going to increase the number of carbons in this to 8. And of course, our hydrogens will be 18. We're still going to react this with oxygen, and we get, in this case right here, CO, carbon monoxide as stated from the question, and H2O, gas. Now just like before, really all we need to do is balance by sticking an 8 in front of the carbon, a 9 in front of the water, and then of course, wait a minute, right. So then we have 8 and 9, so that's 17 oxygens. For some reason I was multiplying 9 by 2 in my head, which that doesn't work whatsoever. So I'm going to use a fraction, 17 over 2. Alright, yeah, I knew I had a fraction for this one, and for some reason I was looking at that and it wasn't making sense. Anyway, cool. So those are basically the complete and incomplete combustion reactions. So for organic compounds, all of them can undergo this, so really it just comes down to balancing. But like I said, with our incomplete, recognizing when we have it. Now let's get into the interesting ones. So the addition reactions. Now, one thing I love about these organic reactions is that their names are fairly evident of what's actually going on. So for addition reaction, we are going to have something that has a double or a triple bond. So basically only our alkenes and alkynes can undergo this reaction. Essentially, we need an unsaturated hydrocarbon. And what happens is that we break that double bond or triple bond and we add new molecules to it, right? Hence addition. So the types of molecules that we can add all of our halogens, so fluorine, chlorine, bromine, iodine. We can add the hydrogen halides, so basically it's still our halogens, but they're attached to hydrogen. we can add hydrogen atoms, so H2, and we can add water. Now for our water, I know this one sounds a little bit weird, but when we look down here, addition of water, notice how I've written as HOH. That's because what's going to happen, we're going to add a hydrogen and the OH is a hydroxyl, so in the addition of water, we actually produce an alcohol. Now, all of the other ones, when we produce halogen, so if we have a halogen or a hydrohalide, as it's called, we get organic halides. And I forgot to put this in, but if we add hydrogen, we can get an alkane or an alkene, depending on what's reacting. So we'll kind of get into that when we get those reactions of the alkynes very shortly. So let's have a look at our first reaction. So we will notice all these right here. I have but-1-ene for everything. Now there is a special note of that if an isomer will form, well, we have to record it. So part of this is being able to predict not just one product, but all the products that can form. And of course, it's not that if isomers can form, they will form. It just depends on the ratio. So the ones that are going to produce isomers in this group, so all of our hydrohalides will produce isomers and water. So when we add bromine, chlorine, fluorine, or iodine, so just the halogens, there will be no isomers. And if we add hydrogen, also no isomers. So we'll kind of get to that example first. Now for the first few, I'm just going to do like kind of structural diagrams so we can see all the bonds and how everything works. So if we have our but-1-ene with chlorine. So but-1-ene is 4 carbons, so 1, 2, 3, 4. Now I'm going to stick the double bond right here. So carbon 1 is the one on the far right. Now when we put our hydrogens, I was kind of debating on just not even putting in the hydrogens because hydrogens just don't really count. But anyway, just for the sake of doing this, we'll add this. And if we're acting with chlorine, I'm going to draw chlorine like this, so Cl and Cl. So the reason I'm putting chlorine like this is that we're actually showing what's going to get added, right? So what happens when they react, what's going to happen, the first thing is that the bonds break in typical reactions. Now don't erase the bonds here, I'm just kind of demonstrating what's happening, all right? So when chlorine reacts with this but-1-ene, the first thing is the bonds break. Now for the chlorine, we break the covalent bond between the chlorines, but we only break the multiple bond between the carbons. That single bond, so the bond between the two carbons right here will not remain broken. This is why chlorine doesn't break any of the other carbon-to-carbon bonds, only the multiple bond. But now we'll notice that if I break this double bond, this carbon right here, so carbon 1 and carbon 2 are now missing bonds. So this is where we get the addition. So one chlorine goes to one carbon, the other one goes to the other carbon. So that's essentially what's happening, right? So when we get our reaction, and it's only going to be the carbons that contain the double bond that will actually react. So we're still going to have our longest carbon chain is going to be but. All of these other ones still get their hydrogens. So once again, I probably should have left them out because it's assumed. I'm going to start line diagram very shortly. But our two new ones here, I'm going to have highlighted in red, is we get one chlorine and one chlorine. So now we have our new product of 1,2-dichlorobutane. So this is why when we add a halogen, we will not get any isomers, is that one carbon that contains a double bond will get one chlorine, and the other one gets the other one, right? So no matter what, we are going to get the chlorines added to those two carbons. Now let's look at some isomers. So if we react but-1-ene with hydrogen chloride. So for this one, I'm just going to switch to line diagram for this one right here. If you want to do structural, you can, or condensed structural is completely up to you. So our but-1-ene, 1, 2, 3, 4, and our but-1-ene looks like that. So same thing, I'm drawing it from right to left, so or numbering it right to left, just so when I add these things right here, it'll make more sense. All right. So just like before, so what essentially happens is that when these molecules collide, right, the double bond breaks and the single bond breaks. Now what's going to happen is that hydrogen is going to go to one molecule, or one carbon, and the chlorine goes to the other one. So if this happens right here, the way I have it drawn out, our first isomer that we're going to get is going to be our butane. Now, as I had it right here, so this carbon right here on the end got that hydrogen. So in line formula, hydrogens are assumed, so we don't need to include it. But the thing that actually matters is this chlorine. So we actually have 2-chlorobutane. Now the thing is, when these react, it's not like the hydrogen chloride, or in this case, like the but-1ene can actually decide, it's like, ooh, I like one of those carbons, like, ooh, I want this carbon, or I want that chlorine, or whatever. Like, they can't talk, they just bump into each other. And the other possibility is that, well, the hydrogen might go to carbon number 2 there, and the chlorine goes to carbon 1. So if we have that possibility, right, our other isomer, now this one right here got the hydrogen, which I don't need to include, but now carbon number 1 here gets that new chlorine, and we have a 1-chlorobutane. And those are the only two possibilities. Now, once again, hopefully you didn't erase all those bonds. I just kind of did that so you can see on why we're getting the alkane. But so now I'm going to put everything back in how originally how it was. So we got the double bond here and the single bond here. So this is how that reaction would look, right? So we have our but-1ene reacts with our hydrogen chloride, and we have our two products. Now, if you want to number your carbons as well, right? We know 1, 2, 3, 4, hence that was name, and 1, 2, 3, 4. And we'll notice carbon 1 and 2 both got those atoms. So now let's look at our water. So the water molecule is going to add exactly like the hydrogen chloride, is that one of the carbons, God, I can't talk. One of the carbons will get the hydrogen, and the other one gets that OH group, the hydroxyl. Now we have to remember it's only going to be the carbons that contain the double bond. So if we have our but-1ene again, reacting with water. Now you can write water like this, but it's hard to see what's actually going on. So I always write water in organic reactions like this, HOH. So we can tell one of the carbons is going to get the hydrogen, and the other one gets the hydroxyl. Now, once again, whether we put the hydrogen on carbon 1 or carbon 2, we have to remember for line diagrams, hydrogen doesn't matter. So even if you're doing structural diagram, you put a hydrogen, it doesn't matter, right? So if, let's say, I go the blue route, so hydrogen goes on carbon 1, so which we don't count, the hydroxyl now, hydrogen on carbon 2, let's put the hydroxyl on carbon 1. So if this happens, I get that, and put in that hydroxyl, and what I just created was butanol. Now the other possibility, I'm going to use a different color now, and I do apologize too if you hear like the clicks of my mouse, so I'm kind of like using a mouse and a stylus and everything else to kind of do this, so I do apologize if you do hear those clicks, but anyway, that's just a part of it. So the other one, crap, I wanted a different color. Red. Here we go. So the other possibility is the hydroxyl goes on carbon 2 there, right? So those are the only ones that can get added to. So if it goes on there, we go carbon 2, and we get butan-2-ol, right? So those are the only two isomers that we can get. So just like before, we'll notice that the maximum amount of isomers that we can get with an alkene is only going to be 2. And it just depends on where we add that functional group. So that's where you just had to be careful that, especially the ones where you're adding hydrogen, remember hydrogen doesn't count, so try not to add it and then like classify it as like hydroxy or something. Like I don't know, I've seen some weird words over the years come up with people trying to like call hydrogen a branch, but it's not, right? It's just part of it. It only matters about like the halogens and of course the alcohol. Now, our alkynes. These are interesting. So what we have right here is but-1-ines. So I'm going to draw a but-1-ine very similar to the other ones like this. Now, when we say react with 1 mole of bromine, so notice with the alkenes, I didn't have to specify 1 mole. That's because if we have 1 mole of bromine, essentially what that means is that we only have 1 mole of bromine. So we only have 2 atoms to add, right? Now, if we only have 2 atoms to add, we only have enough to break only one of the multiple bonds. That's it. So when bromine reacts with this one right here, only one of the multiple bonds will actually break. So what we're left with is we're still going to have a double bond left, but on carbon 1 and carbon 2, that's where we add our bromines. So we end up getting a 1,2 dibromo but 1-ene as the product, because we only had enough moles of bromine to break one of the bonds. All right? Now, once again, you can draw this out in structural diagram as well and see that if we only add 2 atoms, right, carbon 1 and 2 is still going to be unsaturated. So this is where we have to be careful about the wording. So when we see 1 mole, right, we're only adding 2 atoms. Now our next one, surprise, surprise, 2 moles. So now we're going to double the amount of bromine available. So that means if we have our but 1-ine again, so now what we have is actually 2 moles of bromine, so it looks like that. So instead of only adding 4 atoms, instead of adding 2 atoms, we get to add all 4, right? So the first bromine group, when this gets added, so that will break kind of the first double bond right here. So, and then the second group, right, that I'm just going to underline in blue, that's going to break the other multiple bond right here. So then what we're left with is now we have an alkane. On carbon 1, we get 2 bromines, and on carbon 2, we also get 2 bromines. So we get the name is a 1,1,2,2 tetra bromo butane. And that is our product. So now, and I know I don't have an example here of the hydrogen halides, so that's one I actually don't want to show you, is if we add 2 moles of a hydrogen halide. That one is kind of in your workbooks, I think, and it will kind of show up. So that one will have more than 2 isomers. So when you get to your workbooks and you get a chance to actually work on it, I highly recommend trying that one, see if you can get it, right? Just because. Now, the last one is, of course, the addition of hydrogen. So this one actually has a very specific name called hydrogenation or hydrogenation. Either pronunciation is fine, although you probably heard the word hydrogenation before, or in some different stuff like hydrogenated oils and stuff like that, so you might have heard that word. So basically it means it's hydrogenated. So what that means is that if we take stuff, so either an alkene or an alkyne, we react it with hydrogen. Now, we still need to be careful for like the whole idea of the 1 mole and the 2 mole, especially if we have an alkyne, right? But for the most part, if we have something like ethene, so CH2, CH4, I can't count, right? If we're acting with hydrogen, which is just HH, right? We can see right here, we're just going to add those hydrogens on. And the new hydrogens I will put in a different color just so you can see what we added. So let's go with red, seeing how it's close to Christmas, right? So these 2 gets added. So in this case right here, we have our alkene going to our alkane. So these are the addition reactions. Now in your workbooks, I do have them labeled the addition reactions with no isomers, and then on the second page with isomers. Now there were 2 mistakes, I think, on the one without isomers. I accidentally created some with isomers. So just hop on Google Classroom, and I updated like basically some changes that you need to do for the reaction section. So like I said, where I kind of just created that workbook or added onto it over the years, I definitely didn't check my work before I sent that off to print. My bad, but anyway, you know, I found those mistakes, so hopefully that'll fix it. So once again, hop on Google Classroom and see those. Now, that was reaction 1. So 3 more to go. Next, we have our substitution reactions. Now, I don't know, I'll get that UV light thing. So substitution reaction. So as it sounds, we are going to substitute one atom for another one. So what happens is we are going to substitute a hydrogen with another atom. All right, so that's it. So these here are interesting. So the bigger the hydrocarbon, the more possibility for isomers. So normally with the substitution reactions, we see shorter alkanes for this. So UV light is generally needed, and it's required as the activation energy for these reactions. And we can also use heat. We can also use shaking and stuff like this. So this is why when we did the bromine test, it tested great for unsaturation, because for the addition reactions up above right here, no activation energy is required, but generally if you do it at room temperature, there's nothing else we need to activate it. So we don't need UV light, we don't need to shake it, we don't need to heat it. We just add in our halogens and boom, we just get whatever we need. These right here, so generally when we are doing a substitution for an alkane or an aromatic, right, so we substitute it with a halogen. Now, the trick is with this one, we only substitute one atom and one atom only. So that means when we substitute our hydrogen, so notice right here, our halogen denoted XX, so like Br, Br, Cl, Cl. We get some UV light, we get an organic halide, and notice how we get a hydrogen halide in return, right? So that's the hydrogen is replacing one of these X's right here for the halogen. Now, there is a special case as well, is that I've seen this pop up, is that we can get an organic halide reacting with an ionic hydroxide. So basically just OH minus. So this can come in the form of like sodium hydroxide, lithium hydroxide, potassium hydroxide, whatever. Anyway, wherever that halogen is, we replace it with the alcohol, and then we get the ionic salt in return. So basically that means the halogen goes back into solution as an ion. Now we are going to notice at one point this is the exact same setup for a different reaction. So this is why for a substitution reaction, if we're doing the substitution of an organic halide, I will be very specific that it's supposed to be a substitution reaction. All right, now let's look at some of these right here. So methane reacts with chlorine. Now, as noted, multiple isomers can form, so just be careful. So if we have our methane reacts with chlorine. So as mentioned on the previous page, one hydrogen, one chlorine. They substitute each other. That's it. So, and once again, on methane, where there's only one carbon, there's not going to be isomers in this case right here. So what we end up getting is our chlorine, the three hydrogens that are left, right? And we get this chlorine right there. And then the other product is we're going to get the hydrogen bonded to the chlorine, the substitution reaction. So we end up getting chloromethane in return. Now when we get something like propane reacting with bromine, so propane right here, I'm going to go back to line formula. Now this one we're going to get isomers. So as we can tell right here is that bromine can potentially take a hydrogen from carbon 1, right? Now if it also takes it from the other end right here, we're going to get the same product, right? So this is why there's only 2 isomers for here, so you want to like exhaust all your options. So really the only options right here is bromine can take a hydrogen from carbon 1, or, I'm going to go different color right here, or it can take a hydrogen from carbon 2. And of course with both of those we get 2 different products. So the first product that we can get, right, so it's going to be like this, is we're going to get 1 bromo propane. So that's product number 1. Product number 2 we'll get is going to be if bromine replaces a hydrogen on the second carbon. So 2 bromo propane. And finally our last product is HBr. So that hydrogen it took pairs up with the bromine. Alright, so of course we cannot forget about our aromatics. So benzene can also undergo substitution reactions, and this is the only reaction we're going to see with our benzene. So in this case right here, just remember with benzene on how every carbon right here only has 1 hydrogen. So when we do a substitution reaction, pick any carbon we get chlorobenzene. So that will be the substitution reaction there, right? And of course, I could have put that chlorine anywhere and I'll get the same product, right? Now, obviously, let's say we start off with phenol, PHENOL, right? Technically still aromatic, technically still has that benzene ring, and those hydrogens, not on the oxygen, but it has to be a carbon-hydrogen bond, could be substituted. So we could end up getting like a 2-chlorophenol, 3-chlorophenol, 4-chlorophenol, and so on, right? So once again, in the workbook, there'll be 1 or 2 of those kind of sprinkled in there for you to try, but this is just kind of starting off learning the ropes. Now, the other one, now these right here are going to be our 2 substitution reactions of our thing. Now, once again, we are going to learn another case where it's not going to be a substitution, something called elimination, but once again, I will specify which ones it should be, and you know, if you're given a diagram of a full reaction, you can tell which one it was as well, right? So if we see it's something being substituted or something being eliminated, which I know we haven't done elimination yet, so calm down, we'll get there. So for 2-bromopropane, it's going to look like that. Now react to sodium hydroxide, so whenever we see this, right, metal ion, this will always be a spectator ion. Right, so kind of like in our acid-base section is that metal ions didn't react. Just like in organic is we're not going to have metal ions reacting. So whenever we see metal in organic, it's not important whatsoever. So the hydroxide ion is the big one right here that's going to react. So in this substitution reaction, we substitute our bromine with the hydroxide. So what we end up getting, there's going to be no isomers for a substitution of organic halide. So we're going to get our propantuol, and the other product is going to be the ion of bromine, right? So it just kind of replaced it. Now an example like this one, so I want to toss in one kind of difficult example. So we have 3-iodotoluene, which toluene is just a common name for methylbenzene. So what we have, and yes, I'm fully aware that this isn't following the normal convention. It should be 1-iodo-3-methylbenzene. So, whoops. Let's fix that. First mistake I found in those. Oh well. Whoops, so 1-iodo-3-methylbenzene. So put our iodine anywhere, and carbon 3, we have our methyl. Now, because this is reacting with lithium hydroxide, same thing, only the OH. So in this case right here, just like the other one, only the halogen is going to react with the hydroxide. That's it. So our product turns into this, which is 3-methyl phenol, and then our other product is I-. So that's where we have to be careful with that, right? And knowing when the substitution or what it substitutes. So this right here is, I'll let you guys kind of come back here and do this one at another time. I'm just going to go through the other reactions so then we can see this, but this is just kind of giving you an idea on the last time. This is a very typical process as well, or a typical type of, it's almost like choose your own adventure book type thing where you have organic materials process and type of reaction. So there's different answers right here. I think so. Okay, Rue. Nope, I don't think so. So there's only one reaction. Never mind, forget I even said anything. All right, let's look at our next one. So esterification reaction. So this one is a reaction of, and if you're keeping track of the organic families we're touching, carboxylic acid and alcohol. So far we've seen alkane, alkene, alkyne, and aromatic, so all of our hydrocarbons. Now we're getting into some of our derivatives. So this is the carboxylic acid and alcohol, so we are going to produce an ester and water. Now normally in this one right here, we do need a catalyst, and we will do this reaction at some point as well, which our catalyst is H2SO4. So if you're reading a reaction and it says like with a catalyst or with, H2SO4, it's just a catalyst, don't worry about it. Now, this reaction is also generally called a condensation reaction because water is produced. So this is going to be a common trend we're going to see. So essentially what we have is our carboxylic acid plus alcohol produces our ester and water. Now, in this reaction, so what actually happens is the carboxylic acid loses its hydroxyl group, and the alcohol loses the H from the hydroxyl group, and that's what forms water. So then the alcohol kind of bumps on over and then bonds with the carboxylic acid. So when we have ethanoic acid, so a 2-carbon carboxylic acid reacting with propane-1-ol. So there's a reason I drew my propane-1-ol like that. The reason for it is that I'm going to highlight how we get our water. So as stated above, the carboxylic acid loses its hydroxyl group and the alcohol loses its hydrogen. So this is OHH. Well, this is our H2O. So that's the first product that we can put in, right? So that's our water. Now our ester, well, notice right here, so this is that C double bond O group. So what you need to do is imagine this oxygen going over and now bonding with this carbon. So what we end up getting is that 2-carbon chain from the carboxylic acid. Now from that C double bond O, it bonds to that oxygen. Now how many carbons do we have attached to that alcohol? Well, it was propyl, so we have 1, 2, 3. So we have propyl ethanoate. Now the best thing about these right here is that when we're given ethanoic acid, basically nothing will ever change from the carboxylic acid. So all you need to drop is the ic acid and add O8, and you have your parent chain named. Now that is not going to be the case for the alcohol, because if we get like a propane-2-ol, we get some interesting stuff. But luckily no isomers, and we see a propane-2-ol right here. So no isomers for these reactions either. So let's do pentanoic acid react with methanol. So pentanoic acid is 1, 2, 3, 4, 5 carbons long, and we have the carboxyl functional group. Same thing, methanoic acid. Now you don't need to write it like this. This is just what I do because I really like seeing two of these together, so I know that's lost, that's lost. So then we get our H2O, and then our ester. Will look like that. So we have methyl pentanoate. Now, as I just mentioned not too long ago, if we have an alcohol on carbon 2, or the hydroxyl on carbon 2 in the alcohol, it gets a little tricky. So, let's scroll on down. Now, just for this right here, just do this, guys, because I don't know why I did this. Just scratch out the 3-bromo-4-methyl. You know what? Who cares about the branches at this point? Because the important point of this one right here is actually what to do with the propane-2-ol. So let's just have propane-2-ol reacting with pentanoic acid. So scratch out those branches. So for our pentanoic acid, so I just redraw what I drew up above. So pentanoic acid will look like this. Now normally our propane-2-ol, right? So if we drew it like this, it's going to be hard to see, right? So what I'm going to do is actually rotate this around. I want to get the hydroxyl group facing the carboxyl group. Now, if this is supposed to be carbon 2, this is carbon 1, and this is carbon 3. So it's important why I drew it like that as well. So now, basically, when we lose these, right, to form our water, my parent chain is still going to look the same, right? That pentanoic acid. But now, when it's attached to that oxygen, so you'll notice right here, I'm basically going to redraw this. So I have a bond going to this carbon. We have a carbon up there and a carbon down here. So what I actually just drew, right, keeping track, now our pentanoic acid isn't going to change, But remember, when we're naming our esters, carbon 1 is always attached to that oxygen, right? So now carbon 2 is going to be down there or up there, so it doesn't really matter which one you choose as carbon 2. Essentially, all that matters is that we have a methyl ethyl pentanoate. So these are the ones that you have to be careful with, is that if we have the hydroxyl group on a carbon 2, on a carbon 3, and so on. That's what you just have to be careful for. And if you do want to call it 1-methyl ethyl, you can, although it's a little redundant because we can only get that methyl group on carbon 1. So that's just one of the things that you do need to be careful for. Right, so make a little note to yourself. If the hydroxyl group is on carbon 2, 3, 4, 5, or 6, you're going to get a funky branch off your ester. If it's on carbon 1, basically like this one here, methanol, turn it to methyl, right? The one we had up here, we had propanol, turns into propyl, right? So that's how the esters get, how they form. And once again, hopefully we will get an esterification reaction either before the Christmas break or shortly afterwards the Christmas break. All right, our last set of reactions. So if you're keeping track of the families we've touched up on, so alkenes, alkanes, alkynes, aromatics, carboxylic acids. Now we'll notice esters, I know we're not going to do reactions of esters, so technically we covered esters, so esterification covers esters. So technically 6 out of our 8 families are done. Oh, alcohols right too, so 7. But alcohols are the only ones that actually double dip in the reactions. But now we're going to look at elimination, and this is where we're going to get organic halides as well. So I know it's not on this page, but when you go through, organic halides will be on the other page. So let's look at elimination reaction. So this is literally the reverse of an addition reaction, right? So in addition reactions, we broke a double bond to create carbon-to-carbon single bonds, and we added 2 atoms. So in elimination reactions, we are going to remove atoms. Right? So that's what we have right here, the removal of atoms or groups of atoms from adjacent carbons. So the key word here is adjacent. So what this means is carbon next to. And that's important because it's going to remove, essentially in all these right here, it will remove a hydrogen from an adjacent carbon and is adjacent to the carbon that contains the functional group. All right? So that's important to know, and I'll highlight this when we go through. So we are going to get 2 products or more. Isomers may form. Now normally we need a catalyst like sulfuric acid, aluminum oxide, phosphoric acid, basically, a catalyst. So the first we're going to look at is the dehydration or elimination of the hydroxyl group. So all we need for this one is that we will have an alcohol. So notice acid. So when it says acid right here, basically it's H2SO4, strong acid, which I know back here we had carboxylic acid. So if we have an alcohol and a carboxylic acid, that's esterification. If we have alcohol with acid, don't make up a random carboxylic acid and toss it in there, right? Don't do it. Do not do it. Use H2SO4 if you want to identify it. So what we're going to get is our alkene, and dehydration, we get water. So let's have a look. Butanol. So butanol is going to be 1, 2, 3, 4 carbons, and carbon 2, I have my hydroxyl. Arrow. H2SO4. All right. Now, when we look at our functional group, which is this one right here, so the hydroxyl functional group. So as it's stated up above, is that in an elimination reaction, we remove the functional group and an adjacent hydrogen. So this is why when we look at OH, right, hydroxyl, if we put another hydrogen on there, right, we magically get water. So we need to have another source of hydrogen. So where the hydroxyl is going to pick up the hydrogen, it's either going to come from carbon number 1 or carbon number 3, because these are the only adjacent carbons. So that's why the word up here, adjacent or next to, was so important. So isomer number 1, and let's actually put this as a different color so we can color code the difference. All right, so let's say we go the red route right here. So what's going to happen is that we still have our hydrocarbon chain. But what we're going to get is, because we removed the hydroxyl from carbon 2 and we removed a hydrogen from here. So what's going to happen is that if we remove 2 atoms, then we get a carbon-to-carbon double bond, and we get but2ene. The other possibility that I had in pink, hopefully the colors I'm choosing actually shows up on the whiteboard. I never thought about that. Like, they're very bright and vibrant on my screen. I just hope they actually show up fine on the whiteboard and you guys aren't like just, squinting and trying to figure out what colors I'm using. Anyway, the other possibility is our functional group was right here on carbon 2, right? And the other adjacent carbon was carbon 1. Well, if we remove the functional group and the hydrogen from the adjacent, then we're going to get a double bond formed between these two, and we get but1ene. And then, of course, our other product, H2O. So those are the elimination reactions. So you need to look for adjacent carbons. Now, not every reaction is going to have an isomer, right? So if we have cyclohexanol, looks like that. Now, we will notice that whether I take a hydrogen from here or a hydrogen from here, we get the exact same product because there's no branches. So as soon as I draw this, I just created cyclohexene, right? So I don't need to say cyclohexone because it's assumed, right? Carbon 1. So in this case right here, no isomers. So that's why you always need to look for adjacent carbons and also have, that naming background in the back of your mind so you know exactly if you only have one product or not. Now, the last one we're going to look at, so once again, something where you can get some isomers. So methylheptanetol reacts when exposed to an acid catalyst and heat, right? Those details are irrelevant. We have our methylheptanetol. Why did I go so big with that one? 1, 2, 3, 4, 5, 6, 7. So on carbon 3, we have a methyl. On carbon 2, we have the hydroxyl. Now, once again, we always look at our functional group, hydroxyl, and we look at, well, do I have multiple adjacent carbons? If you only have one adjacent carbon, you're not going to get isomers. But here, we have 2 adjacent carbons. So I have carbon 1 and carbon 3. So if I have 2 adjacent carbons, that means I'm going to get 2 isomers. So isomer number 1 is if I go in red, so I lost functional group, I lost a hydrogen right here, so I get my double bond between carbon 1 and 2. So I have a 3-methyl hept1ene. The other isomer that I'm going to get is that if I lose my functional group off carbon 2, but the hydrogen off of carbon 3. So then I get a double bond going here, and I get a 3-methyl hept2ene. And of course, water being produced as well. Right, so this right here, we have 2 organic isomers. So this is only going to happen, you're only going to get isomers if there are adjacent carbons. That's it. All right, so our last one that we're going to learn, it's still an elimination reaction. So we're still going to eliminate crap. But what we're going to do is we're going to eliminate a halogen. Now, this one is going to be a little different. So the removal of a halide is we need to have base or hydroxide. Now, I know what you're going to be thinking right now. You're like, well, didn't we just see a halogen with a hydroxide and that was a substitution? Well, yeah, you did. So here's the thing. It's if I'm asking you to predict a reaction, if it's an organic halide with a base, I will tell you if it's a substitution or an elimination. But if you're given reactions, right? So you see reactant and product, and you have to name what the reaction is. You have to know if we had an organic halide undergo an elimination reaction or a substitution reaction. All right? So that's why it's brought up both. Now, the reactants are the same. That's the thing. Now, probably you're wondering is like, well, how do you get it to go either way? And that is a really good question. I'm not sure off the top of my head. Either way, when we look at our product, we're getting our alkene, we're getting water, and the halide ion. So make sure to remember the products. So when we have chloroethane reacting with hydroxide ion. So chloroethane, if we want to draw it, looks like this. Now, when we look at the carbon that contains a functional group, this one. Now, when we look at it, how many adjacent carbons are there? There's only one. That's it. So if we only have one adjacent carbon, we are going to get ethene, which we can just draw like this, I guess. Then we get water, and we get the halide ion. No, that was awkward. I'm pretty sure if you want to go. That'll be fine. But either way, only one adjacent carbon, so one isomer. Now the next one, same thing. So 1-chloro 3-methylcyclohexane. All right, let's have a look at this one. Now, when we look at this one right here, so this is the carbon that contains the functional group. Now we will notice there are two adjacent carbons. So when there are two adjacent carbons, that means we are going to get two isomers. So, isomer number 1. So I'm going to keep the drawing the same. So isomer number 1, if we remove the chlorine from this functional group and adjacent carbon off that one, we get this molecule. So remember, in cycloalkenes, carbon 1 and 2 is always across double bonds. So we got 1, 2, 3, 4. So we have a 4-chloro cyclohexene. Now the other product, right, is if we lose the functional group off this carbon and the hydrogen off that carbon. So if we lose it here, here's the double bond now, and we get a 3-chloro cyclohexene. And our other two products, water and the chloride ion. So that's where we have to be very careful with the isomer stuff. All right, so where does this leave us? How to recognize organic reactions. So basically, it's the family, right? Addition reactions, alkene or alkyne. That's it. Substitution reactions, alkane or aromatic. Esterification, carboxylic acid and alcohol. Elimination, alcohol and organic halide. So that's how we recognize what type of reaction. So it's all about the family. And the only one that double dips is the alcohol. But that's where you need to pay attention to what is it reacting with. Is it a catalyst or a carboxylic acid? Right? If it's reacting with carboxylic acid, esterification. Catalyst, elimination. So that's how we recognize our reactions. Now the trick is, I know this was a lot to take in, right? So if you do want, and I don't know if I was going through this too fast or not, but if you do need to re-watch the video I have up on Google Classroom, you can slow it down, and I think I pretty much have the exact same reactions. I might have drawn it out a little bit differently, but either way, right, it's there for you. The thing is right now is that with the reactions is you need to go in your workbook and practice, right? As you're finding out with organic chemistry, yes, it's a lot to memorize, but the more practice you get, you will burn it into your back of your head at some point, right? So right now, you guys are free to try some of these right here, right? So we have some practice, right? So 2-bromobutane plus a hydroxide ion. Now, I completely forgot to put in what this one should be, so make sure we call this one Let's go with elimination. You know what? I just made a liar of myself because I said I will tell you what I wanted it to be, and I forgot to put that one in. So, whoops, sorry about that. Right, so here's a few practice on picking those up. And then we can see some old diploma questions here as well on the end. So try those, and then of course, oh, let me go back there. So just try those and open up your workbook and try those. So just start with whichever reactions seem like it might be a good introductory to just get used to it. Open up your workbook to that page and start in with it. But I gave you multiple examples, so I have them in your workbook where they are labeled on what type of reaction. And then I also have a mixed one where you just need to pick out what type of reaction it is. All right? So I'll let you guys work, and hopefully I'll be there tomorrow to answer any questions. And yeah, so put it this way. I'll put this up on Google Classroom, but if I'm there tomorrow to answer your questions, we'll still review. Quiz will be on Wednesday. If I'm not there tomorrow, there's no way I'm going to have a quiz if I'm not there to help you guys out. So we'll probably try to move it to Thursday or after the break. My vote is for Thursday, just because try to get it done before the break. And that way, our unit is after the break. So either way, if I'm not there tomorrow, immediately the quiz will be moved to Thursday. If I'm there tomorrow, sorry, it's going to be Wednesday, but make sure practice, practice, practice. So that's it. I'll let you guys get to work. All right, hopefully see you tomorrow.